Well, hi guys. We are starting our next unit, and this is expanding on series. That we're now going to have something called power series, and I'm going to teach you how to build them today. And over the course of the next 2 weeks, we're going to talk about why we use them, and we're going to talk about how to take just a handful of known polynomials and use them to build polynomials for even more, bigger and badder functions, I guess. So anyway, let me tell you first of all what a Taylor polynomial looks like. A Taylor polynomial is a polynomial, so you're going to have increasing powers of x. So these are going to be x's with powers on them, and they're going to be separated by plus or minus signs. So let's take a look at the general form for a Taylor polynomial. The nth degree Taylor polynomial has this form, and this will be centered at a. What's in parentheses there, those a's, that's the center. So this is centered at a. So what I mean by that is the x coordinate we're looking at is the a. So for example, if we were centering this at 2, all of those a's would be replaced with 2's. I want to stop for just a second because I know this looks pretty intimidating, and I want to take a look at just the first 2 terms of this. I want you to take a look at this right here. Now, I hope that looks familiar, because what is that right there? That is just our tangent line equation, f of a plus f prime of a times x minus a. I realize this big bad 1 factorial is down there, but don't worry about that. And what a Taylor polynomial is it keeps adding more and more terms on, and it's a powerful way of approximating functions if we need to approximate them. So we just add on to our tangent line equation, and you just keep adding on terms. So the derivatives keep going up in one degree. So there's a second. This is like the second degree Taylor polynomial right here that stops at the quadratic. You've got the second derivative. If you take the first 3 terms, now you're, well, actually 1, 2, 3, 4. If we go all the way out to there, I see a little boo-boo here too in this little definition. Right here, this should be a 3. There's a little boo-boo there. So if we take a look at the first 4 terms, this is called the third degree Taylor polynomial. It's called the third degree because we have an x cubed, and it's dealing with the third derivative as well. So you might answer questions in class like write the first 4 terms or write the third degree. You're going to see that here when I do a couple examples. Alright, so let's take a look at why we have these. So I'm going to go to a little graph here, and we're going to build the cosine function today. So I want you to take a look at this. Here is the graph of cosine of x, and what you're going to do is you're going to see increasing powers of that Taylor polynomial. So let's watch this movie. There's the first degree, it's just the line. There's the quadratic, there's the quartic, there's the 6th degree, and then the 8th degree. So what I want you to see is as we add more and more terms onto the Taylor polynomial, the polynomial starts to converge onto the graph of cosine. And as a matter of fact, if we take this all the way out to infinity, we have a polynomial that will actually equal cosine x. So you can see we get to out here to the 30th degree, and we almost matched it. Let's take a look at it for the exponential function e to the x. Start with the first degree, that's just 1 plus x. Now we have the quadratic, and then the cubic, and then the quartic, and then the 5th degree, and then the 6th degree. And you can see that it's starting to converge onto e to the x. Let's take a look at it with sine as well. Here's a graph of sine. And as you start to build the Taylor polynomial, the more and more terms you get, you start to become, it starts to converge onto the graph. So that's what Taylor polynomials are. Alright, so let's just practice some. Let me close this, and let's head back here. Alright, so this is the condensed form of the previous page. We're writing this. This is called a power series. And this is a power series in x. So this is the condensed form of what you just saw before. The n in parentheses up here, this means for the number of derivatives you take. So like if there was a 4 here, it would be the 4th derivative. All right, now a Maclaurin series is a special kind of Taylor polynomial. It is always centered at 0. Centered at 0. And you'll understand what the centered part means here when we start building these. So you see all of these data points come from values at 0. All right, so here we go. Let's just build one. We want the Taylor series for cosine of x about x equals 0. That means centered at 0. So this has a special name. Since it's centered at 0, this is a Maclaurin polynomial. So here we go. Maclaurin polynomial looks like this. F of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared. We'll go one more. Plus f triple prime at 0 over 3 factorial times x cubed plus dot 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 all the way out to the nth derivative at 0 over n factorial times x to the n. So let's just build this. Since cosine is my function, I need to find f of 0 or the cosine of 0, and that of course is 1. Now the rest of this asks me to evaluate its derivatives at 0. So let's find, since f of x is cosine x, let's find some derivatives. What is f prime? Well, of course f prime is negative sine. What's f double prime? Well, f double prime is negative cosine. And then what about the third derivative, triple prime? Well, that would be positive sine. And then the fourth derivative, now I'm done making tick marks, I just put a 4 in parentheses. The fourth derivative is right back where we started, at cosine x. All right, so we want the first derivative at 0. So here's the first derivative. F prime at 0 is negative sine of 0, which is 0. F double prime at 0 is negative cosine of 0, which is negative 1. The third derivative at 0 is sine of 0, which is 0. Look what's happening on these odd powers. On the odd powers with the odd derivatives, we're dealing with sine, and so those terms are going to end up canceling. So let's find the fourth derivative at 0, and our fourth derivative at 0 is cosine of 0, which is back to 1. So I think we've got the pattern here. So let's see if we can't build this. Our Taylor polynomial is f of 0, well, that's 1, plus f prime of 0 times x. I'm going to go ahead and write this in there. F prime of 0 was 0 times x. And then plus f double prime of 0, which was negative 1, over 2 factorial times x squared. And then plus the third derivative over 3 factorial times x cubed. And then plus the fourth derivative, and that would be over 4 factorial times x to the fourth. And we're going to keep going, and you're going to get this general term is going to be negative 1 to the n times x to the 2n over 2n factorial. And we'll start that one at 0. So we get our Taylor polynomial for cosine is the summation from 0 to infinity of negative 1 to the n times x to the 2n over 2n factorial. And that is exactly equal to cosine x. Okay, let's find a Taylor series for a polynomial centered about x equals 3. So this will be f of 3 plus f prime of 3 times x minus 3 plus f double prime of 3 times x minus 3 squared over 2 factorial plus f triple prime of 3 over 3 factorial times x minus 3 cubed plus dot dot dot. So let's see here. Since f of x is x cubed minus 10x squared plus 6, I guess I need to find f of 3. And that's going to be 27 minus, because 3 cubed is 27, minus 90 plus 6. And so that is equal to, what is that? Negative 63 plus 6 is negative 57. All right, now we need some derivatives, so let's go ahead and find some derivatives. F prime of x is 3x squared minus 20x. So f prime at 3 is 3 times 9, well that's 27, minus 60, and what is that, negative 43? No, it's not negative 43, it's negative 33. Yeah. All right, well, how about the second derivative? The second derivative will be 6x minus 20. So the second derivative at 3 will be 18 minus 20, which is negative 2. What about the third derivative? Well, that's just 6. So the third derivative at 3 is 6. And what about the fourth derivative? Well, now we're at 0. And the fifth derivative, all those after that are going to be 0. So let's see if we can't build this here. All right, so our Taylor polynomial is f of 3 plus f prime at 3 times x minus 3 plus f double prime at 3 over 2 factorial times x minus 3 squared plus f triple prime at 3 over 3 factorial times x minus 3 cubed, and then all of my terms after that disappear. So let's see if we can't clean this up a little bit. So I'm going to have negative 57 minus 33 times x minus 3. And this is going to be minus 1 times x minus 3 squared, and then 6 divided by 6, that's also 1, x minus 3 cubed. So there we go, we've built it. And if you have the time, you should go ahead and maybe distribute all this and collect all your x's, and you're going to get right back to this right here. I think that's a good exercise. All right, there's 3 that you need to know that that are very, very important for now. We're going to build on this later. And those 3 are e to the x, cosine x, and sine x. And this is their condensed form. Let's take a look at what they would look like as expanded. If we plug in 0 for n, x to the 0 is 1, and n factorial 0 factorial is also 1, so the first term here is 1. Then if you plug in 1 for n, you get x. And if you plug in 2 for n, you get x squared over 2 factorial. And then if you plug in 3 for n, you get x cubed over 3 factorial, plus x to the 4th over 4 factorial, plus dot, dot, dot. That's pretty easy. And then for cosine, we had 1, then minus x squared over 2 factorial, and then plus x to the 4th over 4 factorial, and then minus x to the 6th over 6 factorial, plus dot, dot, dot. That's sort of an easy pattern, even powers of x's. Now for sine, this is going to be x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, and then minus x to the 7th over 7 factorial, plus dot, dot, dot. Sine deals with the odd powers of x. All right, let's answer one last question here, and then we're going to have some more tomorrow in class. This is from the College Board 2007, I think, test. Doesn't matter. But we've got a bunch of information about a function here, h. We've got h's position at 1, 2, and 3, and its derivatives at 1, 2, and 3 as well. And question A says, write the first degree Taylor polynomial for h about x equals 2. Well, that will be h of 2 plus h prime of 2 times x minus 2. That's just the tangent line equation. So we just can pull all this information from the table. H of 2 is 80. H prime of 2 was 128 times x minus 2. So that is the first degree Taylor polynomial. And now we're going to approximate h of 1.9. So h of 1.9, notice there's no way I could find h of 1.9 because I don't know the function for h. But I could approximate it with this Taylor polynomial. So h of 1.9 is approximately equal to the Taylor polynomial at 1.9, which would be 80 plus 128 times 1.9 minus 2 is negative 0.1, which is 80 minus 12.8, which would be what is that, 67.2? There's no way I could have figured that out exactly what h is because I don't have the function for h, but I can approximate it. All right, let's take a look at the next one. Write the third degree Taylor polynomial for h about x equals 2 and use it to approximate h of 1.9. All right, the third degree looks like this. H of 2 plus h prime of 2 times x minus 2 plus h double prime of 2 times x minus 2 squared over 2 factorial, and then one last term, h triple prime of 2 times x minus 2 cubed over 3 factorial. So let's see if we can't get those pieces of information. H of 2 is 80. H prime of 2 is 128. H double prime of 2 is 488 thirds divided by 2 is 488 over 6. And then H triple prime of 2 is 448 thirds divided by 6 is 448 eighteenths times x minus 2 cubed. There we go. That is the third degree Taylor polynomial. I'm not going to plug in point 1 because I don't have my calculator here. This was a calculator question this year. But that is the third degree Taylor polynomial. And by the way, let's go back and answer the second part for A. For A. Is this approximation greater than or less than h of 1.9? Well, since my first derivative is positive and my second derivative is positive, that means our graph is concave up. And I just did a tangent line to a concave up graph. And where do tangent lines where do tangent lines fall? This is below the graph. So this is too low. All right, so tomorrow in class you're going to be building some of these, so I will see you guys then.